And, je donne la parole à Yann, du coup, qui va être le chairman de la session explicabilité. Donc, je peux juste présenter Yann comme étant un des leaders scientifiques du projet DEEL côté Québec.
Merci Grégory. Merci Grégory. So, yeah, hello everyone. Welcome to this session on explainability. I mean, Grégory already mentioned this morning like the promises that machine learning holds, especially for like the performance that it can accomplish for complex tasks. But for safety critical applications, sometimes, most of the time, performance is not enough. So we need robust performance, but we also need to somehow build trust into the system. In many cases, when we resort to machine learning to solve a complex task, it's because all the other classical approaches have failed us somehow. And that means also the concepts that we know to talk about the process or the data or the phenomenon at stake, well, basically didn't help us in predicting or programming a system for that task. So when we resort to machine learning, we get another option to model the system, but then it comes at a certain price. So if we want to explain it, and all the concepts that we had didn't help us so far, now that we have a model that performs well, there's a question of still trying to explain it. And these explanations are crucial for the machine learning expert to understand and debug the model. It's crucial for the domain expert as well. Towards process of certification, it's going to be important for regulatory authorities as well. And also, it's useful for the end user because in many cases, we don't need just a prediction. We like to understand somehow some context or some importance or some kind of beginning of explanation for the decisions that's been made. And well, for a complex task, I mean, it's a question, can we give simple explanations? And you can try to explain the whole model, or you can try and ask if you can explain an individual decision. These are also very different questions. Maybe one way is to directly go for some models, transparent models, whose decision process is somehow directly understandable by a human. But these are usually hard to learn from data. And in that setting, usually they yield, or they might yield lower performance. So we can be tempted to use other models with much more capacity, which yields that performance, but then whose decision process is much more obscure. So I'm very happy to have like 3 speakers this morning about explainability. They'll tackle for us some ideas in that direction for providing methods for interpreting models in various ways. The first speaker is Nicolas Brunel. He's professor at NZ in the Evries Lab for Mathematics and Modeling. He's also the scientific director of Quantmetry. And he will talk about explicabilité du machine learning, passer du local au régional pour améliorer l'estimation et la compréhension des modèles black box. Maybe Nicolas, I'll let you translate it into English if you want. Yeah. So please welcome Nicolas Brunel.
À la pause, okay. Thank you.
That was short, very effective. Do we have the slides?
Yes, it should be. Okay. Yeah, maybe if you can go. Okay, great. So just to. Okay, so thank you, Yann, for this very kind introduction and for this kind invitation to this great journey to explainability in machine learning. So I will present you. Okay, so one way to go from a local to a regional explainability and a set of what we think good reasons to do that. So this is a work, presentation based on the works of Salim Amoukou, that is a PhD student that is about to finish his PhD at Stellantis. And okay, so we have two works in it and other works on the way. So just to remind and in a way to reformulate what Yann has just said about what do we compute explanations. So maybe some kind of new questions that arise from the use of AI is to be able, we as statisticians, mathematicians, or data scientists more generally, to be able to give some interesting answers to these kind of things, meaning that I was recommended a movie that I don't like, but I don't know, or I was refused my mortgage, and I want to know why. So what's important with explainability is that, in a way, the way that you have to answer to the question really depends on the context. And obviously here the context is really different, that you don't have the same energy and you don't expect the same kind of answer, the same kind of tools for answering to these two questions. And this is one part of explainability. So explainability really depends on the context, but explainability, or what we call explainability, also depends on the people who wants to be explained. So typically you have 4 profiles that ask for answers. The first one is the AI developer, and usually will ask what is the important variable in my model. You have then the operator that will use the AI, but then he just want to check that the behavior of the AI is parallelizing the knowledge he has about his business, about what he has to do. You have the AI user that just want to have a simple answers and to say, okay, why did it happen and what can I do to change the decision? And then you have a regulator. And usually you can try to find different answers for these different questions. And in a way, what you would like to do is to maybe to make a link, or to try to have a link between the kind of the different answers that you can provide to these different actors. So we'll start in a way by the easy part, which is the what we could say the developer way, where when you look at this classical statistical framework, you could say, okay, I have my data D, I have okay data generating process, and then I have also my D features, and I have a model that I have learned from the data, which is F. Okay, good. And then the question that you had before is typically, okay, where was the pointer? Okay, I can't find the pointer. Okay. So basically the question that you have is that, okay, why do I have this y hat? Because I am xi. So you don't know really, and what usually what we do is that when we have a very simple model, so we can go either for globally or locally, and if you have this linear regression, you would say, okay, I can explain or measure the importance of the feature xg by looking at beta j here to this value, and if I want to go for local explanation, I can look for this kind of thing. Okay, and the thing is that you have a more complex model, and you want to be able, in fact, to explain in a simple way all kinds of different models. And industry really looks for this kind of 3 kind of properties. When you look at variable importance measure, it's something that is model agnostic, so that you can do it systematically. You can compare it, and you can choose as an AI builder and an AI developer. Okay, the kind of models that you prefer with respect to the measures that you have computed. It should be easy to compute, and it should be easy to interpret. And easy to interpret is Okay, always depending on the piece, on the people. And for doing that, Shapley value is usually thought to be a good approach to build this kind of variable importance. And okay, in this talk we focus only on tabular data, and because okay, it's another story if you have really different tasks. Okay. I will remind very briefly what is Shapley value, because I suspect that a lot of you know a bit of the story or how it works. But basically, okay, it starts from a cooperative game theory, and the question of asked by Shapley, and the solution is to say, okay, so I have D players that plays in a game. So a game, a cooperative game is okay when I have a set of D players like that. A game is a value function that is defined on all the possible subsets of the players, and you associate a value to a coalition. And then the question is to know, okay, what is the fair attribution that I can give to the player J, and the answers that satisfies to different properties asked to be good properties and fair properties is the Shapley value, that is just the mean of the impact of J on every coalition that you have. Okay, so this is a weighted mean, and this idea is applied successfully, I would say, for explainable AI in the following way. So you replace players by variables, and you compute, and you select the proper value function to compute the effect and the importance of your variable J. Okay, so you can do that globally, and you can have the Shapley effects, and usually, and we focus especially on that. You have the local Shapley value that gives you for a given observation X. Okay, you take for this value function the conditional expectation. So you okay, very standard approach, and it has been used now for a long time. Just to explain, and the reason of success and why we love it is that we have this very simple linear representation. So that comes from the property of the Shapley values, so it's easy to read, and this kind of representation gives you the opportunity to make beautiful drawings, beautiful figures to explain your black box model. So you have base rate, your beta 0, or your expectation for the population. You have the output, and you have the effect of your different variables, and you can compute it. So this is the easy story, and that everybody likes, because you have also this a nice library to compute that. But we have some problems when we need to compute the Shapley values. The first one is that the computational cost, because you have a sum over all the possible subsets. So, okay, so first thing that you need to deal with. And then you need to compute all these conditional expectations. And this conditional expectation, it's not so easy, because you need to estimate the conditional probability, and you need also, because it's an estimation, you need to control somehow the statistical efficiency or the statistical quality of your estimates. And one problem also is that if you take two observations in different places, but not too far, the explanations can be different. There is no control on that, so in a way your intuition can be a bit messed up. And what was interesting is that despite this computational complexity, you can have a very efficient algorithm called the tree-shap that was proposed for computing the Shapley values for a tree-based model. So you have a polynomial algorithm, and it's really, people love it. Data scientists in the companies really love it, because you have this linear decomposition, it's easy to compute, fast, and you have the beautiful boxes. So we will say that it's not so easy, and in fact, if you focus really on what is really computed and how you can really interpret these Shapley values, you think that maybe, there is some room for improvement. Okay, so if we focus on the tree-based model, so this is a simple tree. So FM is a value predicted for the leaf LM, and the question that we ask here is that, okay, so what is the accuracy of this tree-shap algorithm that is used in a lot of situations, and what is really the do we really compute local importance? Okay, so if you go deeper in the details, so in fact, computing your conditional expectation like that means that you need to compute the sum over what we call CSX. They are what we say the compatible leaves. Compatible leaves mean that the leaves that are compatible with a condition like here, and then you need to detect this set of leaves that are compatible, and you need to compute the probability of a leaf, the conditional probability. And so this is a problem that you need to solve and you need to do. And what is done in the tree-shap algorithm is that it does it in a very efficient way, computationally efficient way. It computes the probability of each leaf by following each branch of the tree and by doing this computation. And in a way, you have a kind of Markovian factorization of the probability along the node of the tree. And so, in some cases, it can be true, but in general, it's not the case. And so, you have a discrepancy between a general approach and what we can do is that we have proposed a slightly different estimator. Is that instead of using this tree-dependent approach, what we have said that, okay, if you want to compute, we compute that. So in fact, we just replace the equality condition, so this condition, by saying, okay, instead of having XS exactly, I take all the guys that are in the compatible leaves, okay? And I just compute this frequency like that, frequency of number of observations in the leaf LM, on the number of observations that are compatible with my condition. And this is not too hard to compute. And if you do that, you can significantly improve the estimation of your Shapley values. So if you take this very simple example, so you have X, you have Gaussian observation, you are in dimension 5, you have a very simple linear model to explain, you learn a random forest. And in that case, you can compute the exact Shapley values. And we use, for comparing the estimates, this relative mean absolute error. And what you can see is that the tree-shap algorithm, because of this very strong assumption that is made on the probability of each leaf, is really biased and with a large variance, while the leaf estimator is biased because we regroup a lot of observations that are not exactly satisfying the condition, but nevertheless we can reduce the bias. And this bias and this error increases with the correlation. So this is a well-known limitation of Shapley values that it's strongly dependent to the dependence of your variables. Another remark that we can make with the standard Shapley value is more fundamental and conceptual. Is about do I have really a local measure of the importance of a variable? So if you take this simple model, so this is in dimension 5 still, and you switch with respect to the sign of x5 either to this simple 2D regression or the other one. And then, okay, so now what is locality? I mean, in my mind, that locality, if I want to compute, for instance, the importance of the variable x1, so it will, okay, for a given observation, when, say, x5 is negative, I want to have x1, x2, and x5 to be important, but I do not expect to have x3 and x4 to be important. I mean, if I have a local measure, I would like to have only information about that. I mean, it's my intuition, how I understand locality. But you can compute exactly the theoretical Shapley value, and the Shapley value is different from 0 in that case. And it really depends on the behavior of x3 in a completely different part of the feature space. So, in fact, in the Shapley value, you do not capture only what happens close to your guy, to your observation, but also in the whole feature space. So it makes it really not easy then to interpret, because if you have a value that is different from 0, Shapley value that is different from 0, you don't know if it's because of your estimation error, or you don't know if it's come because you are estimating also some effect from another part of the. So the Shapley value, okay, is great, it's useful, but it's not completely reliable. And if you look at statistical accuracy, you can feel a bit embarrassed. So one way is to go for to stick on the global approach and to say, okay, if I want to stay global, so I know that I have some results, for example, for the Shapley effects or for some predictiveness measures, that for which you can have statistical properties shown, that you can have consistencies, and you could be at least happy on that side. And so I have, and typically you have this kind of importance measure where you evaluate the importance of AJ by removing this observation AJ. So if you focus on that part, on you say, I want to be statistically correct, then a good way to have a variable importance measure is to say, okay, then what could be great is to split my feature space in different parts, L1, L2, Lm, and then I focus only, and for instance, for the R2 measure, predictiveness R2 measure I showed you, is on each subset, subregion of the feature space, I can compute a global feature importance, and so that I split and I have a good, efficient, and regional local. So it's a good way. But now the problem is for this approach to be interesting, I need to find a proper LM. I mean a proper region where all the observations have the same behavior, and it should be big enough to have enough data so that I can have still a correct statistical inference effect. And so if I can find this kind of big region, but not too big just to remove the bias, so I have some kind of classical bias variance trade-off, it will be great, and it will be quite informative by itself. So the question is, how can I find this kind of region? And for doing that, we have different effects, different tools to compute or extract this kind of regions. The first one, what is really central for our analysis, is to compute what we call the same decision probability. So the same probability was introduced for analyzing what we call probabilistic circuits, and it just measures the following things. So for classification, so you have an instant x and y. And the same probability is just the probability of keeping the same decision just by keeping the feature XS. So, and what you can do, so it was introduced for classification, and you can do that for regression. And for regression, you just add an additional parameter, t, that says the amount of deviation that you allow around what you have measured for x, the y. And you allow for deviation t to say that I keep the same decision, but you can still compute that then easily. And the second concept that we need is to what we call the concept of sufficient explanation. So it's quite natural. So the SDP, the same probability, depend on the subset of variables that I keep to keep the decision, and the sufficient explanation is. Okay, for a given instance xy, it's the subset of variable S star pi associated to the probability pi such that my SDP is greater than pi, and there is no smaller subset that already reach pi. Okay, and in practice, what we do, you take 90%, and you start with a null set in your model. And you compute this SDP for each variable, then for 2 variables, for 3 variables, and until you reach your 90%. And usually in tabular data, in tabular data set, you can have around less than 10 variables can be enough just to reach this 10%, this 90% level. The third thing that we are interested in is to convert this subset of important variables of also to have an idea of the range that I can allow myself to keep the same decision, the amount of variations of the x variables to keep the same decision. So this is only what we call, a rule. So it's just a rectangle for which we associate a prediction value yr. And so if I can show you a small picture of what happens. So if you have the moon data set, the 1 and the 0, and you want to compute the sufficient rule for the black star. Black star is with 1. What you can do is that, you can compute the SDP, and the SDP in that case is equal to 1. If you know x0 and x1, of course. And what happens is that, obviously, you can see that the way you can vary in x1 and x2 is not the same. And what you can do, and what we do for identifying such sufficient rule, is that we look for the close guys, the similar guys, and just we want to find the biggest region, so that we have the same SDP. And if we go a bit too far, then the SDP will decrease, and in that direction also. And so this is the kind of idea we want to identify a subpopulation and the region in the feature space where you can maintain your SDP. And so this is what we call a sufficient rule. A sufficient rule is a rectangle where that depends on the active variable. So in our case it was 2, but it's really a sparse set of variables whose SDP is quite high. And what you say is that basically all the guys, so all the coordinates that are in your rule have a SDP that is greater than pi. And if you go back to the previous example, that you still have this switching regression, and you have and you add 45 other noise variables, and you learn a random forest. So meaning that you have a random forest with 50 variables, and you want to compute the SDP and to detect what are the important variables. And the important variables should be the same as before. And what this is the kind of thing that you will obtain is that you say you can have a rule that says that if x1 is in that interval, x2 is that interval, x5 is negative, then my probability, my SDP is more than 90%. So you can locate to say if I allow such kind of variation, then you can guarantee that you are almost the same. And in that case, you can compute that the SDP for other variables is very, very low. And you can do that for, so we have made some comparison with other approaches with Shap, Lime, and Invase in the ability to detect in the previous models. Are you able to detect the important variables, so the 5 variables that are already active in the model, depending on the region, and also that to be sure that you don't have a Fuzzy-Curvy rate, that you are not too perturbed with a noise variable. And what seems to be interesting is that this sufficient explanation is able to have a relatively good trade-off from true positive rate and the further discovery rate. And we can also detect that we still have good prediction performance when we use the sufficient explanation. In a way, it's normal because the sufficient explanation and the rule that is built locally is made to be very close to your model. So if your model is good, then your prediction rule locally, that is very simple, should be also quite good at predicting. So you do not destroy a lot of quality in your by using your explainability. So in a way, what's important in the story is that with Shapley value, you only have something that, this variable is important, but you don't know exactly what is the real impact, what happens if you build a model based on important variables with a Shapley value. Oh, you have an answer here. The MSE is not very good. So you do not select really a good predictive model. But in our approach, we try to still have a good predicting model. Okay, so this is experiments that we have done on real data set, so I will not discuss that. But now what's important is, okay, so this is a possible use of okay, what you can have, and the question is, how can we estimate all this quantity? Because surely it's very computationally intensive and you need to estimate it. And you can estimate it by using random forest. Okay, and what's important when you is really to be able to estimate the same decision probability. So the same decision probability in the case of regression is just, okay, means that you need to estimate the conditional CDF of your model for all the possible subset of variables. So this is the quantity that you need to estimate properly. And in order to do that, you can use two results. The first one is, okay, is what you do with the classical quantile regression forest, where you can adapt the random forest to compute the CDF. And the other challenge is computational, is to be able to compute, okay, you have this guy, can compute this guy efficiently, but you need to be able to compute for all the possible subset of variables. So it can be very, very, very heavy to compute. And so we use the approach developed in the paper of Schaff about that uses the projected forest, where you can find a way to project easily by every subset. So in the paper, it was about the expectation, so we adapted to compute the CDF. And so if you do that, so we have an estimator that is a locally adaptive estimator of the conditional CDF, where the weights are computed by only using the variable in the coalition S. And what you can show is that you have a convergence, almost sure convergence of your SDP by using a random forest and just adapting the random forest algorithm. Okay, and so finally, so we have moved to the standard random forest that computes a mean prediction to SDP forest, and the SDP forest computes and the SDP and but through a partition of the space. So this is the kind of information that you get, and then when we build finally the rule, we just need to find the biggest rule that satisfies our condition. That is the condition is to be to have a probability of keeping the same decision higher than 90%, and you can find this this big rectangle like that. And identifying then the region is just all the work is done with the random forest approach and with the partitioning algorithm of the random forest. And then we just need to glue all these different parts. So, so the story of this talk was really to move from this local and to regional approach. So what we wanted, in a way, is to have a kind of integrated approach. So that, okay, you compute variable importance, and data scientist will be happy because it will help him to understand well. But then, with that, you are able to identify this region homogeneous of observation having the same behavior, and with a rule set based approach, so that the AI operator can understand it quite easily. And then the next move, and that we are still underway, is to say, okay, so we can adapt this regional approach to move it to something that is actionable for the user. And so you can turn that SDP is controlling the probability of keeping the same decision. So if you want to help the user to change his decision, you can compute the same probability, the same kind of probability to say, okay, you can have a counterfactual, and I compute the counterfactual so that with a given probability, you can reach the values that you want to reach. So you have pretty much the same approach to compute counterfactual rules, and so that you have the same kind of approach, the same indicators that can be used for the developer, for the user, and for the operator. Okay, so this is some papers that was that was underlying the presentation. You have a Python package that can be used for computing the Shapley values in the tree. Okay. So thank you for your attention.
Vous m'entendez? Oui.
Mm-hmm.
Okay. So thank you, Nicolas. Thanks a lot. I think it's already clear after this first talk that giving explanations is tricky. I mean, you need to decide what you want, what kind of estimation, what kind of value you want to compute, and then estimations is also difficult. Do you have any questions for Nicolas?
You use the term regional, so it's not global.
Yes, definitely.
And,
So
do you think you can expand your work to pass from regional to global? Because from some user, what is important is the global explainability, not the local, not the regional explainability.
Okay, so at the end, what we get is that we have a union of rules, meaning that we have a partition, and so that for each part, so I can say it's global, but it's a glue of a different behavior. You have this kind of discretization effect, for sure. Yeah.
Other questions?
Thanks for the great talk. One quick question. If I understand correctly, the sufficient rules are effectively axis-aligned explanations. Have you tested how well this approach works with highly dependent decisions that effectively are non-axis aligned and potentially highly nonlinear, and how does it compare there to Shapley values, for example, for deep neural networks?
Okay, so we don't go for deep learning. So we were really focused on tabular data, and I mean, so we really used this random forest. So random forest, in a way, can be robust to the correlation of the data. So we use this kind of really use that. So if you have highly correlated value, so you will have this kind of highly correlated variable. So it will be you could see it, I mean, in the regions that you have in the correlation of your data.
Thank you.
Hi, Nicolas. Merci pour the talk. I'm here.
Okay.
Hi, all the way at the back. So I'm trying to understand what's going on here, but I'm wondering if there's some kind of possibility that there's some kind of counterintuitive thing that happens when you don't have a lot of data. It seems, is there possible that these sufficient rules regions get larger when you have less data? And is that a problem, or?
Yes, so this is the same kind of trade-off that you have when you want to grow a tree or a random forest, that you have to limit the depth just to have enough data. And we have a way also we need to control, because what happens is that you need to intersect the leaves to compute the condition. And so it can happen that it's empty. So you need to have a control when you compute this.
Okay. Any last question for Nicolas? He'll be back for discussion at the end of the session with the other speakers, so there will be more time for that.